So in this problem, we are solving a mixing model. A 120-gallon tank initially contains 90 pounds of salt dissolved in 90 gallons of water. Brine containing 2 pounds per gallon of salt flows into the tank at a rate of 4 gallons per minute, and the well-stirred mixture flows out of the tank at a rate of 3 gallons per minute. How much salt does the tank contain when it is full? So we have a tank, and this tank has an exit where flow is coming out, and there's an entrance here. And the conditions for the entrance are given. Brine containing 2 pounds per gallon, 2 pounds per gallon. So that means the incoming flow has, per each gallon of the fluid, the brine, there is 2 pounds of salt. This is a concentration parameter, which we denote by C. And since it's going in, we call it C in. So C in is 2 pounds per gallon. That's how salty the flow is. Now, the rate of flow is 4 gallons per minute. Rate, R in, is 4 gallons per minute. So we can immediately realize from the combination of these two that each minute 4 times 2 equals 8 pounds of salt is pouring into this tank. But the salt is dissolved in the brine. So we have, of course, a tank here that has brine in it, and it's being well mixed. That well mixing condition means that the brine is equally salty at each time. So for each value of T, the concentration at this point, this point, this point, this point, at the exit, everywhere is the same. So that's the well mixing condition. Also, another thing here that we have is the rate of flowing out, or out, is given to be 3 gallons per minute. So R out is 3 gallons per minute. So what this means is we are actually losing brine because we are gaining 4 gallons per minute of brine, but we're losing 3 gallons. So this tank is going to, the amount of brine in the tank is going to go up by the rate difference of 4 minus 3, 1 gallon each minute. So the volume of the brine, the mix in the tank, is not going to remain constant. In fact, we can write immediately the equation for volume. The rate of change of volume is going to be R in minus R out. This is conservation of mass. And in this case, it's going to be a constant value of 4 minus 3, which is 1 gallons per minute. That rate of change of volume. So V is the instantaneous volume of the mixture. This turns into an initial value problem because initially at time 0 we have 120 gallons of, well, the tank, the capacity is 120 gallons, but the amount of the initial value is 90, so 90 gallons. So this differential equation can be solved very easily. The derivative of v is just 1. So v should be t plus a constant. And since initially it's 9 a gallon, it's easy to see that v should be t plus 90. In other words, when t is 0, it's 90 gallons initially in the tank. And every minute you add a gallon according to this formula. So this is the volume of the tank as a function of time. It linearly changes. So also at the end of the problem, the question is how much salt does the tank contain when it is full? So we already know that due to this equation and the fact that the capacity of the tank is 120 gallons, then it takes 30 minutes for the tank to get filled. So why do we need this? Because when we study this mathematical model and we try to find an equation for the mass of the salt, which I want to denote it by m of t, the m function. Eventually, I want to know how much salt does the tank contain when it is full. So when it is full, that is the time. So I want the mass when t, the salt mass when t is 30 minutes. So how do we do that? The next step is to write an equation, this time for the salt mass. So if m is the instantaneous salt mass inside the mix in the tank, so what we have is dm by dt is the rate of change of mass, the salt mass. So it's going to be the input rate, just like that, minus output rate. But this time, by rate, I mean rate of the salt mass, which is obtained by multiplying the concentration by the flow rate. So we have C in times R in minus C out times R out. And initially, it says that the amount of salt, so brine containing, so initially it says contains 90 pounds of salt. It's dissolved in 90 gallons of water. So initially, m at 0 is 90 pounds. So let's see how this differential equation, the right side of this differential equation is going to look like. C in, R in, those are given, the control parameters that we have. We have 2 by 4 worth of, which is 8 pounds per minute. That's the rate in of the salt mass pouring into the tank. Let's see how much per minute is leaving the tank. So we have R out. R out is already 3 gallons per minute. But the problem does not immediately specify what is C out. However, C out, which is the concentration of the flow as it's leaving the tank, can be found or should be found using the well mixing condition. Well mixing condition once again means the concentration at each time everywhere in the tank, including the exit, which is what I need here, should be the same. So what is the concentration, the instantaneous concentration of salt in the tank at time t? The well mixing condition tells me that the concentration of the mix in the tank is the same as the C out, the concentration of the flow exiting the tank, and that is equal to, by definition, because it's just a uniform distribution of salt inside this brine resolution, is going to be the mass of the salt, here, m of t salt mass, at time t, divided by the instantaneous volume of that mixture. So the will mixing condition gives rise to this formula. So for C out, I'm going to put it equal to m over V, and V is already determined as a function of t, multiplied by R out, and R out is 3. So the main difference between this equation and that equation, this one is about salt mass, so we have to multiply by the concentration compared to those terms to find the rate of change of the salt mass. So now let's rewrite this differential equation or initial value problem. So once again, now we're trying to solve this initial value problem. dm by dt, so m is now being a dependent function. It's an unknown function of the independent variable t. dm by dt equals 8 minus, so there's another way of writing this, and that's, I can regroup 3 and t plus 90 to make it as a function of t multiplied by m, this m right there, which if we look more closely, we can realize that this is really nothing but, you know, the first order linear equation in standard form, provided that this combination gets moved over to the left side. So we can apply the method of integrating factor for solving linear first order equation in standard form. And m of 0 is 90. So now we need to solve this initial value problem. So moving the exit rate of salt mass over to the left-hand side, we get a first order linear equation which is in standard form. First order linear equation in standard form means you have a normalized derivative coefficient, this one, and this coefficient of m is what we usually denote by p of t, and this constant 8 is what we usually denote by g of t. So the first step to solve this problem is find the integrating factor for this linear equation. To find the integrating factor, we have to write mu of t as e to the integral of this p of t function, which is 3 over t plus 90. And so this is going to be e to the 3. We can pull the 3 out. And dt over t plus 90, this is a linear expression with derivative 1. So when you integrate it, you have to divide by 1. It's using a linear substitution, u equals t plus 90, for example. So we get really e to the 3 ln of t plus 90. I don't worry about absolute value because t is positive the time here in this problem. And I can push the 3 through the power here, through the ln, and using exponential law, I get t plus 90 cubed. So t plus 90 cubed is an integrating factor for this problem. What that means is if I multiply both sides of this equation by the integrating factor, I'll get t plus 90 cubed dm by dt plus multiplying this by this term gives me 3 times t plus 90 squared because of this t plus 90 factor in the denominator, times m, and this is equal to 8, multiplied by the integrating factor. So what we have is now the role of integrating factor once again is the left-hand side becomes the derivative of the integrating factor in m. So this means t plus 90 cubed times m, derivative of that, which is precisely the left-hand side by the product rule, is this function. So simply the derivative is known, so let's integrate both sides to get t plus 90 cubed times m equals integral of this function. Now to integrate this function, I simply realize here that t plus 90 is a substitution, linear expression, and using the substitution, because d of this, differential of this equals dt, I just treat it as a power rule, so it's 8 times t plus 90 to the 4 over 4 plus a constant of integration. Let's call that constant of integration k. So now in order to determine the constant of integration, I realize that m at 0 is 90, so I have to use that condition to find k. So if I plug in t equals 0, the initial time, I get 90 to the 4 times m at 0, which is 90, so once again here, t is 0, so this gives me 90 to the 90 cubed, multiplied by m, which is 90, equals the right-hand side. So 8 divided by 4 is 2. T is 0 here, 90 to the 4, plus k. So this is 90 to the 4th as well, so k should be 90 to the 4th minus 2 times 90 to the 4th, so k is minus 90 to the 4. So now combining everything, what this means is the salt mass satisfies this equation where k is minus 90 to the 4th. So let's divide by t plus 90 to the 3rd to find m. So the salt mass, the instantaneous salt mass in the tank, is going to be, so this is 2 times t plus 90 to the 4. When you divide it by the cube, you get 2 times t plus 90. And then you have this constant, which is minus 90 to the 4th, which should be also divided by this thing. So I can write it as minus 90 to the 4th divided by t plus 90 cubed. So this is really the formula for the salt mass in the tank for this problem. Now, we want to know in this problem how much salt does the tank contain when it is full. Remember that this tank gradually gets full. So, and we, using the fact that V is t plus 90, we realize that it takes 30 minutes to do that. So all I need to do now is to plug in t equals 30. When the tank is full, t is 30 minutes. So at that time, mass at 30 minutes is equal to 2 times 30 plus 90. So that's 2 times 120. So that's 240 pounds minus 90 to the 4 over 120 cubed. This expression can be simplified, and it's going to be an integer. And this turns out to be 202 pounds. So by the time that this tank is full, namely at t equals 30 minutes, there is 202 pounds of salt mixed in the tank.